Hi, this is Jinglu Zhang from Xiamen University. I am here to introduce our work published in ICML this year, entitled Fast Text-to-3D-Aware Face Generation and Manipulation via Direct Cross-modal Mapping and Geometric Regularization. The task we focus on is to generate 3D-aware faces based on the given text description and further manipulating these synthesized faces according to the editing instructions. Compared with the well-developed 2D face generations, text-to-3D aware faces poses additional challenges, as it requires to model the 3D shapes and depict the intricate details of facial components under different poses. Meanwhile, the semantic consistency between cross-modal and cross-view generation is also a main obstacle. To tackle these problems, existing methods often adopt a multi-stage pipeline for high-quality 3D face generation. Despite effectiveness, the training and inference are still time-consuming, greatly impeding their real-world applications. Additionally, some optimized-based methods are limited at efficiency and generalizations. Therefore, in this paper, we aim to achieve fast and accurate text-to-3D face generation and manipulation via direct cross-modal mapping. We propose a novel end-to-end efficient and effective text-to-3D face generation and manipulation network in this paper, termed E3-FaceNet. Concretely, E3-FaceNet is built based on an unconditional 3D generation network called StyleNerve. In principle, we aim to use the text description to impact the whole process of 3D face generation, including the learning of 3D scene representations, that is, nerve, and the subsequent 2D upsampling. We first built a deterministic function to directly map the text description T and the noise vector Z to the 3D aware face image I under the camera pose P. Here, G denotes the generation network. To realize this function, we first extract the features of the description by the clip text encoder and map it to the latent space. Then we modulate the sampled random noise Z by element-wise addition. Subsequently, the corresponding style code W is obtained by a mapping network, which is then used to conduct weight modulation. In this way, we can effectively combine text information with the style code and impact both 3D and 2D representation learnings. However, this injection is still of limited influence, and achieving well alignment between the synthesis and text semantics remains a challenge. Meanwhile, an inherent problem of training a 3D generative model using 2D unpause supervision is the absence of multi-view information. As shown in the right figure, the model tends to generate 3D faces with obvious artifacts and low semantic alignments. To overcome these challenges, we further propose a novel style code enhancer, shortly SCE, and a geometric regularization. Previous studies have shown the varying levels of detail captured by different layers in a 2D image generator. Based on this, we divide the 3D face generation process into two parts. Nerve blocks generate coarse textual semantics like facial contour and shape, and 2D upsample blocks render intricate facial attributes. To enhance the incorporation of fine-grained text semantics and improve the impact of style codes in the rendering process, we introduce a style code enhancer. Concretely, style code enhancer at the ith upsample block will first fuse the input image features with the text feature via a cross-modal attention. Then, this fused feature is used to predict the offset of the style code W and the newly updated code will be used to modulate the current upsample block. Equipped with the style code enhancer, E3-FaceNet can better embed fine-grained text information into the rendering process, as it refines and augments missing semantic information based on both the given text and the intermediate visual features while maintaining the image quality. Additionally, the proposed SCE also enables our model to perform efficient 3D face manipulation. Specifically, we first obtain the predicted style code offset corresponding to the original style code and the manipulation instruction. Then, a simple linear interpolation of these two style code offsets is applied to refine the final offset and facilitate editing corresponding attribute while preserving the overall facial identity of the generated faces. Due to the lack of 3D supervision from the unposed 2D training dataset, a direct text-to-3D face mapping is prone to generate incorrect 3D geometries and shapes of human faces. To address this issue, we also equip our model with a novel regularization on both basic geometric property and high-order geometric features. Specifically, we focus on the point 3D location and normal vector corresponding to each pixel of the rendered fusion map, as shown in the right figure. First of all, we estimate the depth of a ray and obtain the 3D location of each pixel in the world coordinate. Here, PC is the camera coordinate and D is the normalized viewing direction. Then, we perform regularization on the 3D locations. In terms of the normal vector, we tend to approximate the virtual normal to reduce GPU memory and consumption. We assume that local 3D points locate in the same plane of which the normal vector is the surface normal. Therefore, for each 3D point, we select its two neighboring points to establish a plane and compute the normal vector. In this case, we perform regularization on the normal vectors. These two regularizations are designed to enforce smoothness and coherence among neighboring points, obtaining a more accurate representation of the 3D face shape and facial attributes. By integrating these regularizations, our E3-FaceNet significantly enhances face synthesis, achieving a more accurate 3D shape and improved fidelity. To validate our E3-FaceNet, we conduct extensive experiments on three widely used benchmarks, namely multimodal Syllable A HQ, Syllable A Text HQ, and FFHQ Text. We evaluate the generation quality from three aspects. First is the image quality. For example, the reality and fidelity of the rendered 2D face images using FID and KID. Second is the semantic alignment. For example, using the text-image similarity of clip to measure whether the generated faces align with the given description. And third is the multi-view identity consistency. That is, calculating the mean arc-face cosine similarity scores between the face images synthesized from the same 3D face but rendered from different camera poses. We also conduct a user study for the manipulation task for the perspective of identity preservation, semantic alignment, and editing quality. We first quantitatively compare our E3-FaceNet with two strong text-to-3D face methods, namely latent 3D and descript 3D on Syllable A text and FFHQ text, of which the results are given in Table 1. From this table, we can first find that our method greatly outperforms the other two methods under the metric of MVIC, showing great advantages in terms of multi-view identity preservation. Meanwhile, the performance of the SAE is also outstanding. These results suggest that our method can achieve excellent cross-modal semantic alignment. Moreover, retaining high performance, our E3-FaceNet also speeds up the 5-view generations by orders of magnitude. Notably, E3-FaceNet achieves such performance under the setting of zero-shot generation. To examine the editing ability of our method, we'll also compare it with latent 3D and clip face in Table 2. We conduct a user study for this comparison. We can first observe that the identity preservation and the editing quality of our methods are much superior to the compared methods. In addition, the efficiency of our method is still much better than the others. Only takes 0.89 seconds for the 5-view editing. In terms of the visualizations, our book excels in generating high-quality face images with better multi-view consistency and multiple facial attributes, which also well aligns with the given prompts. As for the editing task, our methods can well respond to the text semantics while retaining high quality and multi-view consistency. We also compare our methods with a set of strong text-to-2D face methods on Syllable A. Theoretically, 2D face generation is much easier than the 3D one. However, as can be seen, our method can achieve better semantic alignment than these 2D methods in terms of gender, age, or hairstyles. Furthermore, our method also achieves outstanding performance on FID and KID, indicating that E3-FaceNet has better perceptual quality. These results will confirm the excellent generation ability of our method again. We ablate different designs in Table 4. Compared with the plane baseline, the location loss or the number loss can help the model to generate smooth surfaces and greatly improve multi-view consistency. Meanwhile, their combination achieves better performance. Besides, the introduction of style code enhancer can inject finer-grained text information into the generation process, as evidenced by achieving the highest semantic alignment score. These results can also be well confirmed in the visualization below. Without the geometric regularization, the model tends to generate faces of artifacts, which is most severe under the base settings. In contrast, these regularization loss terms can help E3-FaceNet synthesize 3D faces with clear contour. Additionally, with style code enhancer, finer-grained semantics can be seamlessly injected. For example, the model successfully generates earrings, while other settings fail to capture this attribute. We'll also present a demo for better visual illustration. Thank you for your listening.